Hi, pre-calculus students. Welcome back to my living room. How are you? Whenever I see myself here, now I can see, my hair is messy anyway, but sticking up in some places. How you doing today? We are working on 1.2b. This is symmetry of graphs. Symmetry is very important to us in our lives. A lot of us kind of need symmetry. If you think about it, like maybe in your bedroom, something like that, do you have to have everything even? That is like a form of needing symmetry. And you've studied symmetry a lot. I mean, all the way back to middle school. But of course, in pre-calculus, we're more detailed about it, really taking a look at algebraically what does symmetry mean? And we do the same in AP calculus. If you plan on going on to that, we use symmetry. So it's important that we understand it. We won't be using a calculator for symmetry. And so we'll be using our algebra skills. So let's take a look. Here's the types of symmetry that we're looking at. First of all, symmetry to the y-axis, that is called even symmetry because a graph is even on both sides of the y-axis, kind of like we are when we're standing up. These are often polynomials with even degrees, hence the name even. Okay. B, symmetric to the origin. This is called odd because it's often associated with polynomials whose highest degree is odd, not all the time, but typically. And this is a point symmetry. If you rotate a graph 180 degrees around the origin, around 0, 0, you get the same graph. That's when you look at it, how you know that it's odd. So this is a point symmetry. And notice to the y-axis, that was a line symmetry. Okay. C, to the x-axis, there is no name for that, which kind of bugs me, right? Even, odd, no name, right? And I think it's because in any case that graph is not a function. It does not pass a vertical line test. So this doesn't come up as much, and so they chose not to name it, right? Maybe we can name it after my cat, Princess. We'll have her in the video sometime. Anyway, so we're going to be testing these three types of symmetries using algebra. So just to save space, I wrote the examples down here that we will be doing over here. So let's take a closer look at it then. These are the test points for the three symmetries that we just talked about, okay? So here is a graph, y equals x squared. You know what that looks like, right? And I put 2 points that are on the graph. Obviously, the 0.24 is a solution point, right? From our last section, from our last video, it makes the equation true. And same with -2 and 4. Notice then that these are both solution points on the graph of y equals x squared. And without a doubt, this is an even graph. Notice the even exponent right here. So what does this mean as far as testing for symmetry? That means that any xy point, like 2, 4, that is a solution for this equation, that the point -xy, take a look here, -2, 4, is also a solution. Okay, so I have stars on this test point because we're going to need that to test for even symmetry. Odd test points, right? I made a picture of y equals x cubed. I put on 2 points. Here's the 0.28 and here's the point -2, -8. So notice if you rotate this graph 180 degrees, it takes this positive x and positive y, pushes it into the third quadrant and makes it a -x and a -y. Again, if the 0.28 is on the graph and is a solution point, so is the point -2, -8. And that's true for any point on this graph, not just these two. Meaning if you have any xy point that is a solution in the equation, that -x and -y, that point is also always a solution to the equation. That's what makes it odd. Notice I put stars. This is our test point for testing odd symmetry. Last, x-axis test points, a little harder for students, but I drew a horizontally oriented absolute value. which its function that you're not used to, well, not function, but equation, is written as the absolute value of y equals x, not y equals the absolute value of x, not what you're used to. That's this here. So this function is the absolute value of y equals x. Notice what makes it symmetric over that line, that x-axis, is if you have the point 2, 2, which does make the equation true, that the point 2, negative 2 also makes the equation true, right? So this point is reflected over the x-axis, and in fact, all the points are reflected over the x-axis, meaning that any xy point that makes this equation true, the point x negative y also makes the equation true. Notice I put stars on this test point here. These test points with the stars are what we are going to be using, not our calculator. So what do? I'm going to adjust I'm going to be working in that little space there. So I'm just going to bring you closer to me. Hopefully this works. Oh, I forgot to turn that light on. Let's see if that helps. There we go. A little bit. Get you a little bit closer so you can see. There we go. All right. So what do we do with all this is the question, right? How do you test symmetries? Then you replace x, y in the equation with one test point at one time. To test for even symmetry, you will replace xy with negative xy. To test for odd symmetry, any xy you will replace with negative x, negative y. For x-axis symmetry, any xy you'll replace with x negative y. Okay. Then you simplify where possible. You'll see what I mean when we do some work together. If you returned, when you did your simplification, to the original equation that you started with, then the answer is yes, there is symmetry. Okay, and here's why. If I have an xy equation and I put in a negative xy, and through legal mathematical simplification, I go back to the original equation, this must be a solution point and it must have that symmetry. And same for the other tests. Okay, so if I do my simplification and I do not and cannot return to the original equation, then the answer is no, it does not have that symmetry. Okay, now when we do these problems, these examples together, we do have to use parentheses and be very, very careful with our negatives. Let's take a look. So the first example, x minus y squared equals 0. Okay, let's test for even. Okay, for the even test point, it says wherever I see an x, I put in a negative x, and wherever I see a y, I'm going to keep it. So for this x right here, use plenty of parentheses. This x, I replace with a negative x minus the y, I keep the same. Okay, simplification, I really can't do anything here. I have negative x minus y squared equals 0. Notice that this is not the original equation that I started with, right? I started with a negative x minus y squared equals 0. Can I make this look like the original equation? No, I cannot, right? If I say, well, I need a positive x here, if I go through and multiply everything by a negative 1 so that the first terms are the same, I will have a positive x plus y squared equals 0. Again, not the same. So there is no even symmetry here. Okay, now you could graph it if you want and check, and you'll see that that is true. Let's try odd symmetry. With odd, we go back to the original equation, right? Wherever there was an x, we put in a negative x. Wherever there is a y, we put in a negative y, right? And we use parentheses to do that. So for this x right here, I'll put in a negative x. Be careful here. For this y right here, in parentheses, I replace with a negative y. Okay, now simplification, Yes, I don't really need the parentheses on the negative x minus, all right, take a look here. A negative y squared times a squared is a negative y times a negative y, which is a positive y squared. Is this equation the same as I started with? No. Can I make it the same as I started with? No, I already tried here. This does not have odd symmetry. Let's take a look at x-axis. Back to the original equation. Let's take a look. Wherever I see an x, I'm going to keep it. Wherever I see a y, I'm going to put in a negative y. I'm going to push this down just a little bit because I have closed captioning on and I'm not sure if you could see that. Here we go. Wherever I see an x, I'm going to keep it. Wherever I see a y, I'm going to put in a negative y in parentheses. Ready? So my x stays the same minus my y, I'm going to replace with a negative y. And now I have x. We already determined that this is a positive y squared equals 0. Look at that. I got the exact same equation back. Yes, this is symmetric to the x-axis. Okay, let's try another one. Just going to see again, we're on a bit of a slant if I can. There we go. Okay, our example B, we are going to run through the same tests using lots of parentheses, right? B, x squared times y equals 5. Even. Wherever I see an x, I'll put in a negative x and I'll keep the y. Lots of parentheses. Let's simplify. A negative x squared is a negative x times a negative x, which is a positive x squared. Look at that. I have the same equation. Yes. If you graphed this equation by getting the y alone, it would be symmetric to the y-axis. Let's check odd. Odd, wherever I see an x and a y, I'll put a negative x and a negative y. Let's take a look. We already said that was a positive x squared. Negative y. That's better. There we go. Equals 5. Take a look here. Is this equation and this the same? No, it's not. I have a negative right here. If I tried to multiply both sides by a negative to make the left sides match, the right would be a negative 5. This is no. Let's try x-axis. That would be, I keep my x. Oops. Sorry about that. Keep my x and make my y a negative. There we go. Again, notice I won't be able to get back to the same equation. Let's even write it a little different, right? We're used to our negatives being out front. This would be a negative x squared y equals 5. Nope. Again, not a match. If I try to multiply both sides here by a negative 1, the left-hand side will be a match, but the right-hand side will be a 5 and a negative 5. This is no. The only symmetry here is even symmetry. One more. See, of course, I wanted to make sure to have one of each type of symmetry, right? Here we go. See, y equals 3x. There we go. Even. Wherever I see an x, I'll put a negative x. Wherever I see a y, I'll keep it. Little simplifying. These two are not the same. I can't make them the same. No even symmetry. Odd. Wherever I see an X, I'll put a negative X. Wherever I see Y, I'll put a negative Y. Little simplifying, negative Y equals negative 3X. Not the same, but if I multiplied both sides by a negative 1, because that is legal for me to do, I get a positive Y equals a positive 3X. Yes. These two equations are the same. It does have odd symmetry. X-axis, I'll keep the X and change the Y. You can see right away that these two do not match. If I try to make this Y positive by multiplying both sides by negative, I mess up the 3X. No. Y equals 3X only has odd symmetry. So thanks for joining me today on 1.2b. It's best to do this very methodically, one step at a time, and let me know if you have questions.